Okay, so we're going to run a couple of our t-tests, starting with an independent t-test with the sample data that we have online. In this data, we're asking the question, is there any difference in 100-meter sprint times comparing males and female sprinters? The reason we're using an independent t-test is because, of course, that we're comparing two different groups. Here we have gender as a categorical variable, 1 being male and 2 being female, and then a 100-meter sprint times as a continuous or scale data, here representing the time it takes them to run 100 meters. So we copy and paste this data into SPSS, go to our variable view, make sure that we name the first categorical variable as gender, and that this is listed as the measure as nominal, and sprint time is listed as scale. Again, this is our high level dependent variable, and this is our low level independent variable, our two groups of participants. We're going to go to Analyze, Descriptives, and Explore to first check our parametric assumptions. Namely, here we're going to look at outliers and normal distribution. We're going to copy sprint time into the dependent list because it's our dependent variable, and gender into the factor list. The reason that we do this is because we want to check outliers and normality in the two groups when they are divided. We don't want to consider this whole data set as one whole set. We need to divide them into those who are male and those who are female. By adding gender into factor list, this will automatically divide the two groups up. In statistics, we click outliers, and in plots, we'll tick normality plots with tests. Click OK. We're going to first scroll right down and have a look at our outliers using our box plot. Here we can see that we have two outliers. One as a star is a exceptional outlier, and this one almost definitely needs to be changed or deleted. The second is a suspected outlier, and we may be able to leave this here depending on whether we still meet the assumptions for normality or not. But first we need to get rid of this number 15. So we go back to our dataset, to row number 15. Of course, we don't just want to delete this. Let's have a look and see why we think it's an outlier. Is it human error? Have we put the data in wrong? Or is it just the fact that this value appears to be exceptionally high? It does appear that this value just appears to be exceptionally high. This individual, number 15, is running 100 meters in 23.5 seconds, which is exceptionally slow compared to the rest of the group. Therefore, it sits as an outlier, and I'm going to click delete and get rid of it. Let's go back and run the same test again, then with this outlier deleted. Descriptives, explore, just click OK because everything is already saved. This time, if we go down and have a look at our outlier plot, we see now we only have the remaining outlier as a suspected outlier, number 23 for group 2, in this case, which is the female group. However, of course, we don't want to just immediately delete this. If we scroll up, we will of course find our test of normality output here. Looking at the Shapiro-Wilk, we can see that both of these, the gender 1 and gender 2, that is male and female, have a non-significant Shapiro-Wilk test. That means, of course, that we have passed our test of normality because the distribution is not different than a perfect distribution. Therefore, we do not have to delete the final outlier because we have a normal distribution. Our third assumption is homogeneity of variance, and we test that when we undertake the independent t-test itself. So we're going to go to Analyze, Compare Means, Independent Samples t-test. In here I'm going to copy sprint time into the test variable, the variable that we are measuring the difference in, and I'm going to put gender into grouping variable here. Of course, this is how the system will divide it into the two groups. When you do this, it asks you to define what the groups are. In this case, we simply have group 1 specified as the number 1 and group 2 specified as the number 2. This is just to prevent confusion in the system if you're using more than two groups in your analysis. And of course, this can only compare two groups at any one time. Click Continue and OK, and we'll get our t-test independent samples results coming up here. So the first thing that we want to look at is this Levene's test for equality of variance, or in other words, our homogeneity of variance test. In this case, we can see the significance is again non-significant. It's above 0.05, meaning that there is no difference in the variance between the two groups. It is a non-significant value. Therefore, we will take the equal variances assumed row off the top here. If we had failed Levene's test, this being a significant value, that is, there is a difference in the variance between the two groups, then we would use the equal variance not assumed row and continue as normal. In this case, of course, we're using the top row, equal variance assumed, so we come across and we will find here 3 of the 4 key statistics that we want to report from this test. Number 1, the probability or the significant difference. In this case we see, because the value is less than 0.05, we have a significant difference between gender for sprint time. We need then the direction. In this case the mean difference was minus 1.69 seconds. We can understand the direction easier by looking at the group statistics at the top here. We can see that the mean for the first group for males was 14.3 and for females it was 16.05. Therefore, males appeared to have a significantly greater or better sprint time than females, the difference being 1.69 seconds, as we can see here. Thirdly, we want to look at likelihood, and to do that we look at the confidence interval of the difference. We can see in this case that the values go from minus 3.2 up to minus 0.14. Therefore, they do not cross the zero line, and it appears to be then a very likely effect. Remember that we're not taking into account factors such as smallest worthwhile change just yet at this point in our analysis. So we have a likely change, a difference between males and females of about 1.69 seconds favouring males, and a significant value for probability of 0.033. The remaining statistic that we need is the effect size, that is, determining the size of the difference between the groups. For this, for an independent samples t-test, we will need the t-score and the degrees of freedom, which are both indicated here, minus 2.276 and 21. If we open up our effect size calculator, which I have here, and we go along to the very first tab, Cohen's d. This is the name of the effect size for t-tests. You will notice that there are 2 options here. One, Cohen's d for independent t-tests, and a second for paired t-tests. Because of course we're running an independent t-test, we need to use this output here. So, whenever we use these effect size calculators, we need to only ever put input data into the yellow boxes. Here in this case we need to put in the t-value, which if you recall was minus 2.276, and the degrees of freedom, in this case, which was 21. We'll see here that this will update our Cohen's d value to minus 0.99. Because this is an absolute difference, we can ignore the minus sign. We just know, of course, because we've already examined it, that this favours males. This is saying that the effect or the difference, the size of the difference between males and females is 0.99, a standardised effect size, favouring males. In this case, we need to determine not only the size of Cohen's d, but also where it fits in this scale here. We can see that 0.99 then fits between large and very large. It's above 0.8 and it's below 1.2. Therefore, we would call this a large effect. And we would report it as Cohen's d equals 0.99, and then in brackets we would write large afterwards. Our question was, is there any difference in 100 meter sprint time comparing males and female sprinters? We saw in this case, therefore, a significant difference between males and females, with males running on average 1.69 seconds faster than females, of what was a very likely and large effect. And that was how we would conclude this study.